about the internal structure and evolution of red supergiants. And I'll discuss several challenges that we face when trying to understand their evolution, and including what we can infer about their masses, and hope to stimulate some discussion for after. So I'll start with a brief overview of the evolution of red supergiants, and then I'll discuss some of the challenges involved in using numerical stellar evolution models to understand their properties and evolution. And finally, I'll finish with a few questions that might help to promote some discussion. So let's just remind ourselves of the big picture of stellar evolution and red supergiants. So stars expand greatly after depletion of core hydrogen, and those with initial masses between about 8 and about 40 solar masses may evolve to become red supergiants at some stage during their post-main sequence evolution. Red supergiants are very luminous and are found near the Hayashi line in the HR diagram. And they can exist in different phases of evolution. So either in a thermal expansion phase between the main sequence and helium burning, during core helium burning, or during some later, shorter lived stage. And observations and stellar evolution models both suggest that stars of these masses will commonly die as red supergiants and produce a type 2p supernova. And they're of scientific interest for many different reasons. And this is the reason I guess we're all here this week to discuss. So I hope to promote some discussion on how to best make progress on several significant challenges facing the field. And these challenges will hopefully try to work to improve our understanding of stellar interiors. And this is important for interpreting observations of both individual stars, populations of stars, and also the integrated light of galaxies. And this talk, I'm going to focus on single star physics, but obviously when interpreting data, it's important to keep binary interaction in mind as well. So I'll get on to some important challenges. So the first is mass loss. So red supergiants can lose mass via stellar winds and also through binary interaction. And the physics of red supergiant winds are not fully understood, and their mass loss rates have been a topic of recent research. And I think Emma Biza will talk about this more in detail later on. So to discuss demonstrate the role that mass loss plays on the evolution, I'm included here a figure that shows the effect on evolutionary tracks in the HR diagram. So the black line here shows the standard evolution of a 20 solar mass star at solar metallicity. And the blue and red lines show models with enhanced mass loss rates from this point here onwards. And we see that these models evolve from the red supergiant phase over here back towards the blue region of the HR diagram. And in fact, once the envelope contains less than about 40% of the total mass of the star, any further mass loss will cause a star to evolve to higher effective temperature, as we showed in my work last year. And I think the key point to keep in mind with regard to mass loss is that, generally speaking, if a star loses about 1 solar mass, it will typically remain as a red supergiant. And then on the other hand, if it loses 5 to 10 solar masses, it can evolve back to the blue. So now we move on to convection in the envelope. And so red supergiants sit near the Hayashi line and have very deep convective envelopes, which can be quite difficult to model. So in general, the approach in 1D stellar evolution models is to use mixing length theory with a free parameter called alpha MLT. And in these models, the radius and effective temperature depends on the value of alpha, which can be constrained using observations. So the figure on the right demonstrates this. The solid lines here show evolutionary tracks with alpha equals 1.5, and the dashed lines have alpha equals 0.3. So we can see here that for the same mass, different alpha can change the location of a red supergiant in the Hertzsprung diagram. And the different colors here indicate different initial masses. Related to this, it's worth noting that it can be more difficult to model the energy transport in higher mass stars where convection is more inefficient. And it's also worth keeping in mind that the metallicity and envelope mass also play a role in setting the radius. So sticking with convection, but moving to the core, convection and mixing at convective boundaries is one of the most important uncertainties that currently affect our understanding of how stars evolve, both in general and also applied to red supergiants. So there's lots of research on this topic from many different directions, and it can be difficult to obtain observational constraints as multiple different variables are involved. Convection in general can affect lots of properties in the stars, and for red supergiants, the key quantities that are affected are the core mass and the helium abundance profile in the hydrogen burning shell. And the uncertainties in convection mean that for a given luminosity and effective temperature, the determination of the initial mass that those luminosity and temperature correspond to depends strongly on convective overshooting during the prior main sequence phase evolution. So in order to map to an initial mass, you need to know more about what's going on during the main sequence. And binary interaction will complicate this mapping. So fourthly, the Humphreys-Davidson limit is an observed upper luminosity limit to stars in the Hertzsprung-Russell diagram. And it's indicated by the pink line here in this plot. And these other tracks show stellar evolution models at different masses for a given assumption about rotation, convection, and then semi-convection. And reproducing this Humphreys-Davidson limit at different metallicities using stellar evolution models has been a topic of recent research and may be quite useful for constraining the properties of stellar interiors. And closely connected to the Humphreys-Davidson limit is the luminosity function of red supergiants. And this may be quite a good test bed for stellar evolution as well, and has also been a topic of recent research using both models and observations. And again, at higher masses closer to the Humphreys-Davidson limit, turbulent convection and energy transport in the envelopes can be difficult to model and complicate the problem. And now the masses. So the masses of red supergiants are quite difficult to constrain. So this is from some of my work last year. The figure here on the left shows a sequence of models at the pre-supernova stage in the HR diagram. And the models have the same helium core mass of 4.3 solar masses and different envelope masses. So ranging here on the left here with an envelope mass of 0, corresponding to a bare helium core, over to 25 solar masses on the right, which would appear as a red supergiant. And the right panels show the final mass versus log TF for the same models. So we notice here is that over a very small range of luminosity and effective temperature, the allowed total stellar mass ranges from about 5 up to about 30 solar masses. And this demonstrates that for any individual red supergiant, it's difficult to determine the mass given the luminosity and temperature alone. This doesn't mean that they're all equally probable, that they're not. And for larger samples, we can use statistical arguments based on population synthesis models, but for a single star, this degeneracy will still remain. And we applied this to observations of progenitors of supernovae. And for example, for this individual red supergiant progenitor, we derived a mass, an allowed mass based on the luminosity and temperature of between 4.6 and up to 35 solar masses. So what can we infer about the internal structure of a red supergiant then, given L and TF, the most commonly available properties? So I wanted to highlight 3 key points here. First, we can infer its core mass from its luminosity with some degree of certainty. And secondly, as we just saw, it's difficult to determine the envelope mass. And then thirdly, we don't know its central helium abundance, as that information is hidden away inside the star. And we actually have less of an idea of its central abundance than other types of stars at different evolutionary phases. And so models suggest that red supergiants are common progenitors of supernovae, and they've been observationally identified as the direct progenitors of many type 2b supernovae. And studying red supergiants at the pre-supernova stage has several advantages. The first is very key. We know their evolutionary state, that is, that they're at the end of their life. This breaks many degeneracies that exist for earlier stages. Second, we can compare to supernova light curves and spectra. And then the disadvantages is that there's usually no spectrum available of the red supergiant. And as of now, there's still a relatively small sample size. And so I just wanted to point this out as this is a useful way to learn more about red supergiants and connect to other areas of research. Finally, the ratio of blue to red supergiants may also be a useful mechanism to constrain different evolutionary pathways. So there's some difficulty actually reproducing the observed blue to red supergiant ratio as a function of metallicity using stellar evolution models. This figure here on the right compares the observations indicated by the black crosses with outputs from population synthesis models from binaries in solid lines and single stars in dashed lines. And the different colors indicate different model assumptions. And this kind of study can be quite complicated as it depends on, from the modeling side, convective mixing, rotation, and mass loss. So I'd like to finish up by suggesting some questions that might be good to think about or discuss later on. So first, what kind of new observations could best improve our overall knowledge of the internal structure and evolution of red supergiants? Second, given the uncertainties in the models that we saw earlier in the talk, what can stellar models actually tell us about red supergiant interiors? Third, what else would we need to know to accurately connect red supergiants to different evolutionary phases? For instance, earlier phases like the main sequence phase, and then possible later phases, potentially the yellow supergiants. And finally, what types of new modeling techniques might provide new insights into how they evolve? And so I'll leave it at that, and thank you very much for the opportunity to talk.